Welcome. In this screencast, we make the final turn for home in a Calculus 2 class, and we talk about curves that are graphed with polar coordinates. We've talked about parametric coordinates, where there's a t that defines x and y. Here we're going to talk about polar curves, and so I have to take you back in time. There was a point in time when a teacher showed you a couple of axes, and said, here's a point, where is this point? And you were like, well, it's on the board. And the teacher said, yeah. To get to this point, we have to go over a certain distance, that's going to be called x, and we have to go up a certain distance, and that's going to be called y, and we're going to call this point xy. And not one of you watching this video right now questioned the very arbitrary choice that your teacher made in moving over and then up. All of you just said, well, that's the way we do it, so that's the way it is. But what if your teacher had said, wait a minute, this point is some distance from the origin, some distance from the origin, and that's usually denoted r. But there's lots of points that are that distance from the origin. How do we narrow it down? Well, we're going to narrow it down by rotating by some angle theta from the positive axis here. And we're going to call this point r theta. This point right here has polar coordinates r theta. See, this point is in rectangular coordinates. And it's called rectangular coordinates because when you break things up into overs and ups, you break the grid into a bunch of rectangles. Polar coordinates recognize that there's only one axis in play. It's the pole. And we measure theta by rotating from the pole in a counterclockwise direction. Or if you're British and watching this, an anti-clockwise direction. So if you do things by polar coordinates, your graph paper looks like this. There's an origin. This is the pole. Right? This is the pole. And we measure everything relative to the pole. This is the origin. It's the point 0, 0. Actually, it's 0 and then any angle at all, because you can rotate about the pole, but if you're not going anywhere, you're not going anywhere. It means that when we graph things like r equals 2, we're graphing all of the points that are 1, 2 units away from the origin. 1, 2 units away from the origin, 1, 2 units away from the origin, 1, 2 units. In fact, it's all of these points here. All of these points are 2 units away from the origin. It means that if we graph theta equals pi over 4, well, that's all the points in the world that can be arrived at by rotating by pi over 4. So if we go to 1 on the pole, and the pole is just a number line, so if we go to 1 on the pole and then rotate by pi over 4, or we go to 3 on the pole and we rotate by pi over 4, or we go to -2 on the pole and we rotate by pi over 4, all of these points lie on a line at theta equals pi over 4. Curves look different in polar than they do in rectangular for obvious reasons. So what's the key to converting? Well, the key to converting is back on this page. How do we convert from rectangular coordinates to polar coordinates? Well, to convert from xy to r theta, right? Let's pretend we know what x and y are, and we want to know what r and theta are. Well, how do you get r from x and y? Well, you use the Pythagorean theorem to get r from x and y. How do you get theta from x and y? Well, we recognize that the tangent of theta is y over x, opposite over adjacent. We don't say that theta is the inverse tan of y over x because that's not necessarily true. Once we say inverse tan, we're trapped in quadrants 1 and 4, but we want to be able to have thetas over here, and we want to be able to have thetas over here. Going the other way, what if we know the polar coordinates and we want to know the rectangular coordinates? What if we know r and theta, but we want to know x and y? Well, x is r times the cosine of theta. Why? Because the cosine of theta is x over r. Cosine of theta is x over r. So x is r cosine theta. And similarly, y is r sine theta. This slide has been memorized by so many Calculus 2 students over the years. It is insane. These are important conversion formulas for us to know. We've got to know them. I will take the rest of our time and talk about some pretty standard curves that you want to be aware of so that we can practice converting and also practice our skills with graphing. Let's pretend that we want to graph r sine theta equals 3. Well, wait a minute. R sine theta, that's y. That's this. Here at 3, looks like this. If you take your calculator into polar mode, so if you were to turn your calculator into polar mode, you could graph things that say r equals, so you'd have to say 3 divided by sine theta, but then your calculator would graph that picture. Your calculator could graph r equals 6 over cosine theta plus 3 sine theta. Your calculator can graph that. And if it does, you get something that looks like this. Why? Why do you get something that looks like this? Well, cross multiplying and then recognizing that this is x and this is y. Well, yeah, it makes sense that that ought to be a line hitting the y-axis at 2 and the x-axis at 6. There are some other curves you should be aware of. R equals 4 sine theta is a circle. It's a circle up here. This is R equals 4 sine theta. It's a circle. It's centered at 0, 2 in the rectangular coordinate system, and it's got a radius of 2, a diameter of 4. Well, why? Well, if you multiply both sides of this equation by r, and then you make appropriate substitutions, r squared is x squared plus y squared, r sine theta is y. This is the equation of a circle. Other things you should be aware of. When you graph something that in the y-x system would be linear, you get a spiral. This just continues going, it spirals. This is called an Archimedean spiral, or a spiral of Archimedes. 2 more pictures before we're done. Oh, let's go with colors we haven't used before. If we graph r equals 2 plus 4 sine theta on our calculators, we get something that looks like this. Comes all the way out to 6. This little loop stops at 2 on the y-axis in a rectangular system. This thing is called a limison. It's from the old French word for snail, because when you graph it, it really does look like a snail. And when we graph things like, oh, let's go, that's a flower, we'll go pink. If you graph r equals 3 sine 2 theta, you get something that looks like this. It's called a rose curve. And the length of each petal is 3. It's this 3. Okay, so you should take some time with some of the practice questions and make sure that your calculator can make pictures like this in polar mode. Hope that this is helpful. We'll talk about derivatives in the next video.